Okay, thanks, Sid.
Thank you, Lars. So we are in the midst of a revolution in planetary science, because what's happening is that we're discovering at an increasing rate the existence of planets around other stars. This has been the most spectacular event in the field in the past decade. And it is becoming apparent that planets are common, and perhaps even that planets around about the mass of the Earth are common. It's a little too soon to make that statement with any great confidence, because it's easier to find more massive planets. But the trends in the data, particularly from the Kepler mission, are pointing in that direction. And so it's natural to think about planets that are roughly the mass of the Earth, roughly the size of the Earth, and decide to what extent our planet might be typical, or might be in some sense unusual or special. Now, the NASA mantra is to look for Earth-like planets around Sun-like stars. I must confess that to me, that's a little bit like looking for a McDonald's restaurant in a foreign city. You're likely to find them, but that doesn't tell you very much. However, it is also true that the methods that are used to find planets around other stars don't just work for Big Macs. They also work for cabbages and broccoli and perhaps for sushi. So maybe we shouldn't worry too much. Now I have somebody you have to worry about. So my goal here is to take these attributes, aspects of the planet we know, and decide whether they're typical or whether they're special. So I'm going to go down this list, and I'm going to sort these attributes. In order to do so, I have to say a few words at the beginning about what I mean by typical and what I mean by special. Obviously, it depends on context. There's a famous quote from Feynman in the context of probability theory, where he made the following comment, that when he drove into the parking lot that morning, he happened to find himself behind a car with the California license plate AZR247, and how amazing it was that it would just happen to be that license plate. And so, of course, the point was that how you define what's typical or what's surprising depends on context. That particular license plate may have been unusual. If you were just looking for a particular one, it would have been surprising to find that one, but just the fact that you had a license plate out of the many millions in California was not, of course, surprising. Now, I'm sure all of you think you're special in some sense, but I can assure you that from my point of view, you're typical. Now, if a 7-foot-tall NBA player walked through the door, that would be special, right? Much less expected than a Nobel laureate in this room. So obviously, context matters a lot. So let's now go through these, starting in some chronological sense with formation. Is there anything unusual about us from that point of view? It would seem that the answer is no. We are in a somewhat typical galaxy, in a not particularly unusual location in that galaxy, the Milky Way. We happen to be neither near the very exciting innermost part, nor in the halo. Very typical kind of place. We think that the conditions at the time that our solar system formed were more exciting than they are now. that there were things going on. There may have been a supernova, maybe even more than one. It was exciting. Quite possibly there was a cluster of stars. However, we also think that that's fairly typical of star formation and therefore by inference of planet formation. So as far as we can tell, there's nothing unusual in terms of the galactic or stellar environment. So I'm going to move that guy over there. What about elemental composition and the closely related question of chemistry? In a moment of fantasy, I could imagine all sorts of weird compositions for a planet. I could have, say, a planet which had a niobium core and a boron mantle and a bromine ocean and a uranium hexafluoride atmosphere. So what's ridiculous about that? Many things. The most obvious ridiculous thing about that is, of course, the elemental abundances, which are determined by nucleosynthesis in stars, except, of course, for the hydrogen and helium and, to a small extent, lithium. So the real question here is, what do you expect emerging from nucleosynthesis? And, of course, that has been studied for more than half a century, and we think we sort of understand what stars will produce, that you need massive stars to produce the heavier elements. As you get beyond iron, you are no longer relying on equilibrium nucleosynthesis, and so you get a small sprinkling of the heavier elements. But we know from that understanding of nucleosynthesis that there's nothing particularly unusual about what we see in our solar system and about what we think we infer for Earth. This is both in respect of ratios and in respect of abundances. We know, for example, that it's unlikely to find a planetary system where there is a planet that has the mass of Jupiter but is made of iron. Why is that unlikely? Because that's a hell of a lot of iron relative to the starting material, which is mostly hydrogen. On the other hand, forming a body of order Earth mass out of iron is not so ridiculous. It's just a factor of a couple of orders of magnitude, which is the difference between the masses of Earth and of Jupiter, factor of 320 in that particular case. So the elemental compositions seem to be perfectly reasonable. Now, the related question of chemistry has, of course, to do with the way that those elements combine with each other. So it's more than just talking about the relative ratios of elements. It so happens that for the Earth, for the outer part, the mantle, you can think of that as just a stacking of oxygen atoms. With the other things, the magnesium and silicon, small amount of iron, and other things stuffed in the interstices. And then we have a core of iron. Of course, if you are immersed in the field of geochemistry and of mineral physics, the precise numbers matter and people argue about them a lot. But there's nothing particularly remarkable about the elemental composition as we infer it from seismology, from the mean density of the Earth, and so forth. And so these things, too, seem to be quite reasonable. Now, I will come back when I get to water, which is going to be a crucial point in my story, to deal with the more volatile things. But in terms of the elements that we see most abundantly expressed in the Earth, there's nothing remarkable about them. Small variations, which can be related to oxidation states, can lead to other outcomes. And there's one other thing that I want to mention, because it will be important when we start collecting information about planets for other solar systems, and that is the case where C upon O is greater than or equal to 1. So this is not us, but there will indeed be cases, because there are variations as you look into the interstellar medium of the ratios of the elements, and that one happens to be close to 1. For our solar system, it's less than 1. But there are likely to be places where it's greater than 1, and then you can get diamond planets or other compounds that are rich in carbon, because then, in this case, you don't have a lot of oxygen tied up in water. You can get to the point where you have reduced carbon as part of your planetary makeup. That's not us, but it is kind of interesting and special, and probably will not be that common, but we're likely to find them. I come next to the issue of the fact that Earth has a moon, and associated with that there has been a change in rotation state of the Earth. We think that Earth's moon came about through a giant impact on Earth towards the end of its accumulation. Accumulation process spread out over perhaps 100 million years after the formation of the solar system back at 4.56 billion years ago. To the extent that we understand the architecture of our solar system, we think that giant impacts are a natural part of the process. They're not special. We can't be sure that that's true of other systems, but to the extent that we have information about other systems, we see disturbance expressed in eccentricities that would be consistent with the idea that this is a fairly common thing. And certainly within our solar system, when you look at what we have, it seems like a natural part of the accumulation process. So large impacts will have taken place. One of the consequences of the accumulation process is to give the newly formed planet a certain amount of rotation. And in the case of Earth, if you hit the Earth with a body that is perhaps the size of Mars, perfectly plausible thing, the Earth can acquire a rotation that would correspond to an initial state as perhaps a 5-hour rotation. We now are at 24 hours, which means that something like 80% of our spin angular momentum budget has been extracted through tidal evolution. The moon has evolved away from the Earth, and just to give you a feeling for those numbers, if I use Earth units where the mass of the Earth is 1 and the radius of the Earth is 1 and the angular velocity associated with spin or orbital motion is 1, then for calculating the angular momentum budget, which would be something like this for the Earth, so this will be the Earth. If I do that in Earth units, that's 1/3 times 1 times 1 squared times 1. Okay, and if I do that for the moon, I will not have the 1/3, it's a point mass in Earth orbit. I will have a mass of the moon, which is 1/80th. I will have the distance of the moon from the Earth squared, which is 60 squared. And I will have a 30-day orbital period, so that'll be 1/30. And you can see that this is 1/3, and this is 3/2, so there's a difference of a factor of 4.5 between them. That explains the idea I just gave you, which is that if the Earth started out with 5-hour rotation period and the moon moved away, it would end up with the current 24 hours. And of course, the length of day is continuously increasing, as is the length of the month, and eventually they'll become equal. But my point here is that this is not an unusual outcome. To be sure, there will be other outcomes, including, I would think, even longer day lengths for other planets. But I don't think of the Earth and the associated moon as being particularly special in this regard. You might want to contemplate what it would be like to live on a planet where the day is only 5 hours. That might be a little bit difficult if it takes you 1 hour to commute.
I mean, can you look at Question?
Can you look at Venus? I mean, it has extremely slow rotation, if I'm not an expert.
Yeah, so Venus has a very slow rotation, and that means that one should worry about one other thing, which is that if you're closer to the parent star, you can also lose spin angular momentum because of the tides associated with the sun. And that is part of the Venus story. Now, the Venus story is actually quite complicated because there's more to it than that. I actually think that Venus once had a moon. That's a digression. We can come back to that. But I think moons are actually quite common. And so when I think about this problem and I see a body that doesn't have a large moon, which happens to be the case for Venus, I wonder why it doesn't have a moon rather than wondering why Earth has one.
Question?
Yeah.
A long time ago, there was a book called Rare Earth.
Yes.
Right, that argued that the Earth-Moon system was special in regard to the mass of the moon, because, as I remember correctly, it would stabilize, the moon would stabilize the axis of the Earth, and therefore there would be fewer catastrophes, and it was therefore special for an item which you left off your list down there, which is intelligent life.
Intelligent life is at the bottom, yes.
Oh, pursuit of happiness. I'm sorry.
That's what I mean by pursuit of happiness.
Okay. And then the last item.
But yes, actually, I had that on my list and overlooked it. You're quite right. The Earth's moon does stabilize the obliquity of the Earth, the amount by which the rotation axis varies. So yeah, and I think the moon actually has an important effect on the evolution of life. That's one of the effects, the fact that unlike Mars, there's a limited range in the change of obliquity. Also, tides have a role in the tidal zone if you have ocean and continent, which may be important for life. And then, of course, it's just nice to look at in the sky, right? But anyway.
But does that mean that we shouldn't expect to find intelligent life in any of these planetary systems?
I'm going to sit on the fence with intelligent life. We'll get to that eventually. But I think the moon is common, and so I think that particular condition is not so unusual, in fact.
Thanks.
That's my own personal view. This is not a democracy, right? I get to choose. Heat sources. So one of them actually is tidal heating. And in some cases, tidal heating can be important. That's a little unusual, I would suspect. The other things, of course, are radioactivity and just the cooling of the planet. Now, it so happens that we live on a planet where, by coincidence, as far as we can tell, roughly half of the heat coming out of the Earth right now is due to radioactive decay. You can attribute it to current radioactive decay, and the other half is due to cooling, which can arise from previous radioactive decay or from the primordial hot state of the Earth. A primordial hot state for a planet the mass of the Earth is perfectly natural. It comes about because of the energy of formation, which is large and is much more than enough to heat the planet up. And so you can keep the planet dynamic, keep it having a significant heat flow, convection, and so forth, even without radioactivity. Now, radioactivity is an interesting one and relates back to this because, of course, the uranium and thorium in particular, which are the dominant heat sources now for radioactivity in the Earth, will actually and are actually variable. We know a little bit about this in the nebula. They also depend on the age, that is, on the galactic timescale, how much time has elapsed in the history of the universe. So this will be variable, maybe by a factor of several. And that is of interest, I think, because it does mean that there will be a range of outcomes for planets like the Earth. You can't assume that a planet that's Earth-like in all respects, except for this one, will behave in exactly the same way. You could have 2-3 times the amount of uranium and thorium or less. However, because of the heat that's put in by gravity, and gravity is the same everywhere, you wouldn't expect to have an enormously wide range of outcomes. The outliers where you had very, very high uranium and thorium, which you can't exclude, would be of interest, but I would put them in the special category. As far as I can tell, looking at what we know about Earth and our solar system and what we know about the galaxy, there's nothing particularly remarkable about this one. So, internal structure means the basic architecture of the inside of the Earth, which looks like this. I have myself a mantle, silicates and oxides. I have a core, which is about 1/3 the mass of the Earth, and I have a sprinkling of crust on top. So this looks a little bit like what you would get if you went into an ice cream shop and they allowed you to have 2 flavors and a few sprinkles, right? Very simple. It's interesting that, at least in my mind, I can imagine something much more complicated, something that the Earth isn't. And by the way, we get to this, of course, from seismology and from other geophysical indicators, but seismology is especially important. I could, in principle, imagine something that's much more complicated. And I'm representing it here by the cross-section of an onion. So this would be an onion model. And why can I imagine this? I can imagine this because if it had so turned out that there was a gradation in density with height, of course, with the heaviest stuff at the bottom to be gravitationally stable, it could actually break up in this way. And I think it's interesting that the Earth has turned out this way. And so, although it seems reasonable enough that this is an expected outcome, a typical outcome, if you will, I can't say that for sure, and I think it's interesting that I cannot say that for sure, because I can present for you, out of my mind, not out of observations, a model that would look like this and would stay like this. And that is to say, it would not mix up. So I think the fact that we have a mantle and a core that's relatively simple, and of course the people in the room are hotly debating whether this is a well-mixed system, and in some respects it's not, the fact that we have this outcome maybe had something to do with the trauma of formation. We certainly think that the core formed from a more homogeneous mixture, not completely homogeneous, of course, but something that was a mix of the two, and then separated by a sequence of events, aided by the fact that a lot of energy was put into the system, and it was at least partly molten, and that helps to make the core. But I'm going to put this guy also over here. Even though I have, in my mind at least, the possibility that we're going to find some cases like this.
With the onion skin structure, are you thinking like in stars we have the onion skin because of elements? Are these different elements on the layers? What's the difference?
Different densities. Different mixes of the various components, because these are multi-component systems. In the case of Earth's core, for example, it would be different amounts of elements other than iron mixed into the core. By the way, this layered structure happens in the Earth's oceans with water and salt, and it's called double diffusive convection. Yeah?
Would the magnetic field also be special?
So in that model, you would not have a magnetic field.
Yeah, I appreciate that.
Bill, be short. It's my seminar.
The reason an onion skin will never happen is because chemistry exists throughout the universe too. That's the redox potential.
So I would argue, we can argue this later. By the way, we're sharing the same office, so we can pursue the argument at a later date. I would argue that this nonetheless can happen. You can't decide that just from redox considerations. And I just gave you an example. The Earth's oceans do this with water and salt only. And there's no requirement that the chemical potential of the salt be the same in each layer. It's a system that starts out with stable stratification and just naturally breaks up into a staircase. You can do that in principle with the mantle too. There's no requirement if the layers have poor communication, which they will, that you drive the system towards some geochemical prejudice. Okay, let's get to the biggie, because this is where we're going to do something different. Okay, so we live on a planet which has oceans. Average depth of the ocean, about 4 kilometers. Coverage of the oceans on the Earth's surface, 70%. So keep that in your mind. Here's a number that you can think of as representing the amount of water we've got on the Earth, counted in the ocean. There's also water inside the Earth, and it may be comparable, might even be more. But keep in mind, just for the moment, that number for what we've got at the Earth's surface. The fact that we have dry land, as best I can figure it, is a coincidence. Because there's nothing special in terms of that amount of water that I've just mentioned, which is less than a part per 1,000 by the mass of the Earth. Nothing special in terms of these considerations. There are bodies in the solar system like Ganymede, Callisto, Titan, not as big as the Earth, but they're representative of the non-gas bodies in the outer solar system, where there's roughly 50-50 ice and rock. So Ganymede is roughly 50% ice, 50% rock. I'm using ice loosely here. It's not just H2O, but it's mostly H2O. On Earth, less than 1 part per 1,000. You could imagine bodies that are drier than the Earth. I see no problem with that. So there's something special about the amount of water on the Earth, and there's a remarkable coincidence. The coincidence is that, expressed as a thickness of the oceans is similar to the height of mountains, or more generally, the topographic relief. It's not really just height of mountains, because the reason why the ocean basins below the mean level of continental masses has to do with density differences between continental crust and the Earth's mantle. By the way, don't think of oceans being as deep as they are because of the amount of water. If you took all the water away, you would still have the ocean basins, we think. There's some assumptions in that statement which have to do with the preservation of the dynamic state of the Earth, which I will also get to. But here's my main point. As best I can figure it, we are in a state of remarkable coincidence. If you increase the amount of water on the Earth by a factor of, say, 10, which is perfectly reasonable, you would have a very different planet. And if you decrease it by a factor of 10, you would have a very different planet, I think. And you can certainly imagine a water world where the total thickness of H2O is thousands of kilometers. So where did our water come from? We think it came from the outer solar system. And of course, there are ways of scattering material into Earth-crossing orbits so that the bodies then collide. And we think in the case of our planet that a lot of this was delivered early. Doesn't come from comets. Comets appear to have a different deuterium to hydrogen ratio than the Earth, so we think it's material that's typical of where Jupiter is, for example. But getting that number, part per 1,000 or thereabouts, as best we understand it, is pure chance. And as I claimed, it really matters. It'll change a lot the nature of the planet that you get if I change that number. And I can't think of any reason why it has to be close to that number. Now, I should say, and people from the CIDER group in many cases will know this, there are feedback mechanisms. There are feedback mechanisms because water on Earth is tied into a cycle. That is to say, there is water carried back down into the Earth, there's water that comes out of the Earth by volcanism. But it doesn't seem as though that cycle is so robust that it will work over orders of magnitude. So I'm going to claim that this guy actually belongs over here. Because I can certainly imagine in other solar systems means whereby the water gets delivered, but I can't imagine why it would be in such a narrow range such that you have dry land as well as oceans. Now you might interject by saying, well, what's so special about that? But But I think the fact that we have dry land and that we have oceans is a significantly distinctive thing. You know, it's like the 7-foot-tall NBA basketball player coming into the room. I think that's distinctive enough in the context of my discussion. So that's why I'm going to put the water over to the left.
But you can put a number on that specialness, right? It's 10 to the minus 3.
Yes, well, yeah, something like that. Certainly if you formed an Earth mass planet somewhat further out, you could have had 1 instead of 10 to the minus 3. As to how far you can go the other direction, I don't know. I mean, it's going to be 10 to the minus 6. I don't know.
Is it also a coincidence that the temperature is such that the water is liquid rather than...
Sure, but we think that the Earth formed in conditions where there should not be water, except a small amount adsorbed perhaps on dust particles. So, so you can have fluctuations, obviously. I mean, for example, here in Santa Barbara, or where I live in Pasadena, we're not in the snow belt, but at least in Pasadena it has snowed. Doesn't do it very often, but delivers a little bit. I don't know about Santa Barbara. I assume it's snowed here sometime in the last 50 years, maybe only for half an hour. Okay. I need to move a little bit faster, but actually some of these are so connected with this that I can dismiss them quickly in the following sense. Atmosphere. Now, a significant part of what determines Earth's atmosphere is implicit actually up here. So part of the answer to the atmosphere question is going to be the oxidation state. It's going to be the materials out of which Earth formed. Now, obviously, one of the things in the Earth's atmosphere is determined by something else, and that's oxygen. We believe that O2 is a consequence of biology. So there's also a connection down to here, and so I can't talk about the atmosphere question without linking it to the other things. Now, in terms of oxidation state, I should make it clear what I'm getting at here. It's not obvious a priori whether you're going to have an atmosphere where the carbon is in the form of CO2 or in the form of CH4, which is methane. And that's actually a very interesting question, and people debate that for the early Earth, and you could debate it for the entire evolution as well. Of course, on Earth, we happen to be in a situation where the carbon is mostly in CO2. There's also methane. It's a disequilibrium system. But except, of course, for the way in which it's linked to life and the way in which life may be linked to water, I can't see my way to thinking of this as being particularly special. By that I mean, of course, there are different outcomes, but there's nothing exotic about Earth's atmosphere except the piece that's linked to life, and so we will come to that question later. But I'm inclined to put it over here, or maybe I should put a little symbol for sitting on the fence. There I am, sitting on the fence. Internal dynamics, by which I mean this, is obviously tied to the things I've said earlier. In the case of the mantle, when we think of Earth, we think of one particular attribute, which is plate tectonics. It would seem likely, though we don't know it for sure, that water is important for plate tectonics, and it's even possible, though this is even less sure, that it's in this limited range of water. Put on too much water and I would expect something different to happen. Not sure exactly how that system would behave. It would have volcanic activity at the ocean floor 1,000 kilometers below the surface of the ocean, but I can't see how plate tectonics would naturally emerge from that system. So a few words about plate tectonics. Plate tectonics, to the extent we understand it, and we do not understand it fully, is an efficient way of cooling the Earth. And the reason is that the outer skin of the Earth, the non-continental part, is participating in the circulation. Whereas if you don't have plate tectonics, as is the case with Venus and with Mars and with Mercury and with the Moon and with the Galilean satellites, to the extent we can make a statement about it, in all of those cases, those other cases except Earth, the skin, the outermost part of the planet, is not participating in the circulation. It's called stagnant lid. There is convection underneath. You need convection to get the heat out. But the surface layer is not participating. Water plays a role in several respects. It weakens rocks. It allows the solid yet flowing material to flow more efficiently. It allows for partial melting. And so I think actually that this one also belongs over here, though I'm a little uncertain about that. Why? Because they don't understand plate tectonics. I'm always suspicious of people who claim that they know how plate tectonics works. Once you've got it going, you can see how it keeps going, but how to get it going is, to me, still a puzzle. Dynamo is an interesting one. The interesting thing about Earth's dynamo, which generates a magnetic field because of convection, is that to the extent we understand it, it looks like a close call. What I mean is this, that of all the parameters that go into understanding whether Earth has a dynamo, means of generating magnetic field from electromagnetic induction, all of the parameters that go into that are such that if you change them a bit in my language is a factor of 2, you're in trouble. Obviously, if you change them in one direction, it's even better, but the other direction, you're in trouble, and we're not quite sure enough about those parameters. They have to do with the energy budget. They have to do, in essence, with whether you can keep the core convecting. Over here, of course, it would not. If you started out stably stratified, you may have trouble having that convection at all. If you run out of heat sources, energy sources, you may be in trouble. It's possible, for example, that the Earth did not have an inner core, solid innermost part of the Earth. The hottest part of the Earth is also the part that's frozen. It's true. Because iron freezes when you squeeze it. Even though it's getting hotter, when you squeeze it, it freezes. That inner core, it's only 5% the mass of the core, apparently is playing a role, to the extent we understand it, in the energetics of the current Earth core. And you can fiddle things a bit and it will go away. Or you can fiddle thermal conductivity, which we don't know perfectly at high pressures and for the right composition. And the dynamo may go away. Venus does not have a dynamo. That's not because Venus is slowly rotating. That's a common misconception. Venus is rotating fast enough so that the dynamics of the core would be strongly affected by rotation, even at 243-day rotation period. So this one, I'm going to tentatively say that that one also lies over there. And by the way, of course, the presence or absence of the dynamo affects the evolution of life. Now, you might think I'm headed towards saying that life is special, but I'm not going to say that. I'm not going to say that because, although I'm not really an expert in the field, but pay attention to what people are saying about what's needed for life, it kind of looks to me as though, to the extent we understand origin of life, it's not that difficult. I once was sitting in a restaurant in Westwood back in the late 1970s with Stanley Miller, who did the classic experiments with Howard Urey, University of Chicago, back in the 50s, where they took a mixture of gases and ran an electric discharge through and got amino acids and so forth. So I asked Stanley, how long do you think it took life to form on the Earth? And he said, 1 million years. And I was rather taken aback by that number. Where the hell did he get that number from? But it turned out that it was just sort of, in some logarithmic sense, somewhere between extremely small numbers, which he knew could not be right, otherwise there would be life crawling out of test tubes all over the place, and numbers so large that you would have trouble understanding why life was already quite complicated and sophisticated in the earliest evidence in the geologic record, which goes back to 3.5 billion years. So we don't know the number, but we know you need energy, you need disequilibrium. Water is nice, maybe not essential, but we've got water all over the place. There's water, at least to some extent, everywhere in the universe. Liquid water is not hard to do. There's liquid water even in the clouds of Jupiter. So I actually think that life belongs over here. But of course, I'm rapidly moving out of my sphere of competence. And so now we come finally to the pursuit of happiness, or that is to say, intelligent life. So last year was the 50-year anniversary of Drake's equation. Frank Drake was asked in 1961 as part of an early attempt to look for extraterrestrial intelligence using radio telescopes. He was asked to make an estimate, and so he came up with what's called the Drake equation, which involves a whole bunch of parameters, some of which I've indirectly dealt with. Star formation rate, there's about 1 star per year in our galaxy. That's kind of fast. What's the likelihood of having an Earth-like planet? We kind of think that's quite high. Some fraction of those will be suitable for making life, I would argue. So those numbers look quite encouraging. The tough ones in Drake's equation come at the end of the equation, where there's the requirement that you estimate how long an intelligent civilization will survive. And that's where people really start disagreeing enormously. Numbers can range by many orders of magnitude. And if you thought it was only 1,000 years, I mean, we certainly haven't had the ability to communicate for more than a few decades, to send out signals, I Love Lucy, out into the interstellar medium and so forth. That hasn't lasted very long, and if you thought that was short, if you thought we were going to annihilate ourselves in the coming 100 years or something, that number would be depressingly short, and then you would have only a small number of intelligent civilizations in our galaxy. That might even be the correct answer. After all, SETI has been going now for 50 years, roughly. The actual SETI program that Jotard is associated with a little bit less than that. And they haven't found anything yet, still trying. Let's hope they succeed. That would be the most exciting thing that you could imagine in science, surely, in all of science. That would be the most exciting thing that I can imagine in all of science. So let's hope something comes out of that. But I would put myself again on the fence on that one. But it kind of looks to me, based on the failure of SETI so far, that maybe that really is the problem. The last term or two in Drake's equation on the right-hand side, the probability that an intelligent organism will emerge from simpler life forms may be very common, maybe intelligence less common, maybe even among those the number that actually achieve communication is small, but maybe most importantly there's a difficulty with the time that that civilization survives without destroying itself. So there you have it, and we can have a few minutes for questions.
I'm wondering about something that might come second on the list after Galactic itself, which is the overall system architecture of the solar system versus exoplanets.
Yeah.
Where, as far as I know, none of the Kepler systems have similar architecture to our own.
Correct.
Is that an important issue, or?
So you have to understand, of course, that Kepler still presents us with a bias. And in the people working in this area, there is this hot debate right now, how atypical is our solar system? I don't think we have an answer to that yet. Clearly, there are a lot of systems where the architecture is different. The most obvious difference that we've known about for quite some time is that many of these systems have giant planets close into the star, and that is presumably because of migration and not because that's where they form. So they form further out, maybe near where Jupiter is, and then because of angular momentum transfer between the planet and the disk in which they're embedded, they migrate in. But it's not looking as though that's a ubiquitous characteristic. I agree with you that it might still come out to be the case that the architecture of our solar system is a bit unusual, and in a sense that's related to water, because of course Jupiter played an important role in the delivery of water to the Earth, we think. That doesn't tell you why it should be the number that it is, but it tells you that that's a mechanism. So I think you're making a valid point, and obviously that creates a bit of uncertainty in my story that there may even be issues up here in the actual architecture of the solar system that when we learn more about planetary systems we'll come to appreciate that perhaps we are a little unusual. Yeah?
I think one needs to make a distinction between intelligent life form and complicated life form. There can be many life forms that we consider complicated, like lions or tiger, which we may not consider intelligent. So what would you put about complicated life form on this list? Is it typical or special?
Well, I'm not expert in this area, although I used to often have lunch with Ed Lewis at Caltech, and Ed was the guy who showed that the genome for the fruit fly was very similar to us. And of course, in the tree of life, we're close to fungi, right? So you should love your mushrooms. But so I don't know. I mean, people in that area would say that a fungus is complicated. Kind of is, really.
But then it's not quite intelligent.
Yeah. So this is not my area of expertise. I'm only an intelligent, hopefully intelligent observer of the field. So yes, you can get more complicated, but then I feel increasingly uncomfortable about saying anything sensible. Jackie?
So you put water in the special category, but you put life on the typical category. I thought most people think water is essential for
Yes, and I did say that, yes. But so this comes back to the question of what's special and what's typical. And I've made a somewhat arbitrary judgment that I think it's kind of special to have a planet that has both oceans and dry land. I don't think you need that specialness to have life. You can have life with dry land, with some water, of course, inside. So like with Mars, maybe. Of course, people debate whether early Mars had oceans. I think that's actually a bit unlikely. So that's a little bit of a softness in the argument. But my main point is that I can imagine having life on Europa, which doesn't look at all like Earth. And I can imagine having life on an oceanless Mars, both of which have water. But it seems kind of special that we have this particular arrangement where we have dry land as well as oceans. Because that requires this coincidence between the thickness of the ocean and the topography. And the topography, of course, has to do with differentiation and also with tectonic processes. We think we understand where you get a few. We understand why you can't have Mount Everest being much larger than it is.
The dynamo along the same line, is it essential for life?
No, I would not say the dynamo is essential for life, although it may be essential for the particular outcome that we have.
So isn't the fact, though, that intelligent life took, of order the age of the lifetime of the sun to develop, that it is a rare fraction maybe of all planets with life that would develop the capabilities to. I mean, just in the sense of it were a very efficient process, like you said, life was. You'd expect intelligent, life to develop within, 10 million years. Maybe we would expect just typically that we would be a much earlier stage in the evolution of our solar system. But the fact that we're kind of halfway along.
So that's an interesting question, and that does perhaps relate to the buildup of oxygen on the Earth, which is imperfectly understood. But But you could argue that life, as I've said, is easy and so forms fairly early on. You may have to wait until after all the mayhem has declined somewhat and you're not getting hit on the head all the time. That's what I call impact frustration at the origin of life. But once that's over, maybe life started early, maybe it started over more than once. That's okay. And then the question comes, what are the preconditions to have more complex forms of life, perhaps life that depends on photosynthesis, for example. You don't have to have photosynthesis, but it is a particularly efficient invention in our history. Who knows? I don't claim to know. But you're right that timescales are of interest, and billions of years seem to be enough. And of course, most stars were not formed yesterday. You would be surprised maybe if you found complex life on a star that formed yesterday, galactically speaking. But, okay.
Great.